Is it okay?
Yes, it is.
Yeah. All right. So, hello everyone again. I'm Vladimir Sotnikov from JetBrains, and on behalf of Nikita Petrov, I present you the talk "Search for Optimal Deep Neural Architecture for Gamma Ray Search at KASCADE." So, the first is our motivation. Gamma astronomy enters Pevatron era. We have detected Pevatron photons, and based on what we know about them, it is expected that Cascade archive data contains Pevatrons as well, because their exposure of Cascade is about 50% of the one of Ulha. So it is very likely that we could find Pevatrons there if we will search enough. That's why we are developing modern deep learning architectures to solve the task. So the data from Cascade consists of raw data from detectors, arrays, electromagnetic deposits and muon deposits, as well as their arrival times, and which are 16 by 16 matrices, and also a set of reconstructed features, say energy, zenith and azimuth angles of the primary particles, show their core position, etc. So we have both Monte Carlo simulations and experimental data presented on the slide, which contain roughly which have roughly the same parameters. You could compare them visually. And we have developed multiple neural network architecture to understand which one suits our task the best. So the first one is self-attention multi-layer perceptron, which uses self-attention mechanism. So basically, that's the same perceptron with the addition of self-attention layers after each fully connected layer, and the rationale behind this decision is that the data that we are receiving from Cascade is relatively sparse, and also it's it's not specially invariant, so we could try to exploit some of this information using self-attention mechanism to give attend to some parts of the matrix and give high weights on it. And another slightly similar architecture is compact convolutional transformer, which is an architecture that evolved from language model. Neural networks are originally designed for processing text data, not the images. So the compact convolutional transformer tokenizes some subparts of the input image of the input matrix, and then in the same similarly to the original transformer models, it performs self-attention given the position of each of these each of token which resembles the part of the image, and produces the embedding layers that we will use for predicting the class of the primary particle, be it a proton or a photon. And another also slightly similar architecture is the graph convolutional network, which takes the input data as a graph. It takes irregularities, special irregularities into account. So first of all, it takes into attention the distances between each detector, and given that Cascade have a cutout of 4x4 in the center, and also some of its detectors are not ideally aligned to the grid shape. We could try to provide this data to model explicitly as distances between the detectors, to also exploit again the spatial information, but in another way, using similar but another approach. And if you will try to compare all these models next to each other, we will see that they are somewhat similar. So the key difference between these three models is that they actually process input data differently. So for the self-attention model, it takes just a 1D array of all the detectors. The self-attention model doesn't need to know about the structure of the grid. It doesn't need to know that it was a 16x16 grid, because during the learning phase it should learn the importance of particular deposits throughout the attention layer. And a convolutional compact convolutional transformer takes these images, takes the input data as an image of two channel 16x16 image, and graph convolutional network takes them as a graph. And there are some evidences that actually these models, on the deep on the underlying math level, they are isomorphic to each other somewhat. So transformers could be presented as a graph neural networks, but from the development perspective, they are quite different, because they process the data differently. And compact convolutional transformer is partially invariant because it takes patches of images 4x4 from the input data, and it applies positional encodings to each of these batches. So they are what's inside this patch is invariant, while the patches themselves are not. And both self-attention and graph neural network model are not invariant. They take positional information as a part of the input. They all have similar amount of parameters, but graph neural network requires a bit more operations like per prediction, but the difference is negligible. And preliminary results we have here look very promising. So all of the models have good performance on in high energy spectra. The issue that we could see here is the lack of the lack of Monte Carlo background. So it's hard to us to carefully to estimate the amount of to carefully estimate suppression rate, because the amount of simulated data isn't high enough for us. The model, the models basically filter all of the background we have, so we can measure this carefully. But the fact that they do that makes us optimistic. And that's basically it. So we have developed a pipeline for searching gammas at KASCADE. So it's the full pipeline from training the model to evaluating it on the unenlightened path of the experimental data. And we have tested different architectures, convolutional self-attention and graph approaches to gamma ray search. And at this point, we need more simulation to more carefully evaluate our models and understand which one is the best and what are like weak and strong sides of them. But basically, they have like a good agreement between experimental data and simulations. On simulations, we also have a very like low rate of predicted photons, which is as a sanity check, tell us that the model's results look adequate. That's it. Thank you.